Hello, everybody. We are back with part two of our relative dating presentation. So, if you remember from the last one we talked a lot about laws of superposition um, and correlation, and that the rocks that are found at the bottom of the layers are the older rock, and the rocks found towards the top are the younger layers. Okay, so now what we're going to do is expand on another piece of evidence to support being able to relatively say this is how old a particular rock layer would be. And so that word is correlation, which you heard me mention 2 seconds ago. And correlation is just the idea of saying that something relates to something else, right? So you can always say, give you a random example. My correlation is that as long as the Patriots are winning, that correlates with Mr. Douglas being happy, right? So that's what I mean by correlation, right? So when you're hungry, you can correlate that with that you need some food, right? So a correlation is just a process by where we can connect different events and saying that even though they're in different places at different times, they're probably the relatively same age because of the area where they're found. All right, so correlation is most effective when we use relative dating. It's more effective than laws of superposition and everything like that, but correlating and saying different places are the same age and the same time period. So when we talk about correlation, what we really can focus on are how there are certain types of fossil structures which can be found in two completely different continents. Now, these are separated by the Atlantic Ocean. So what's the easiest way to say that this fossil could be found all in all these areas in Africa here, not just in one small area, but over a very large area? And then over here is another very, very large area where this particular fossil is found. Well, the only way that we could say that and correlate that is that at one point, Africa and South America, if you remember back when we did plate tectonics, were at one point connected as Pangea. Okay, so we can correlate that. So what do we look for when we are correlating out our rocks? Well, we look for similarities in the rocks. How similar are the types of rocks found in the area? We look for rock sequences. Okay, how the minerals make up the rocks, the color, and fossils. Now, of all of the ones that are on here, color sometimes is the more one that we really don't remember. Back when we talked about mineral identifications in the beginning of distance learning, we don't really want to focus in too much on color. So what I want to focus in on right now, more than all of them, is fossils. And fossils are the remains or evidence that something at one point was living. So your skeleton that gets left behind is a fossil, right? We look at dinosaur fossils, we look at fossils of all different kinds of organisms that once lived on Earth. So examples of fossils would be things like bones, shells, even a footprint. A lot of times people don't recognize that or realize that, but a footprint that's left behind is a fossil because it's not necessarily a remain, like a bone, but it's evidence that something was moving around or located at that area at a given time. And the other thing is we can look at some organic compounds, which is another form of evidence or remains, right? Because your DNA is a remnant of who you are or what that organism is made of. So again, we can look here, this right here, this is a skeletal structure of one of the crustacean organisms, like almost like a lobster, more of like, you can kind of make out the legs here and stuff like that, and a little bit of antenna, and there's the tail right there as well. And then over here, you have another dinosaur fossil as well. Okay, so index fossils. Index fossils, if you ever go into the back of a book, a lot of times there's something called an index. The index is the area in a book that tells you what page to go to. It's sort of like a table of contents, but a table of contents has everything organized by what's just in one chapter. An index is very specific, like you could go to the index and look up something like cake recipes, and cake recipes would be found on page 17. So you know to go directly there. And then that pretty much helps you to know where to find something. An index fossil is a fossil that is used to define and identify geologic periods. So this is our best method for correlating rocks' ages. So for example, this is called a trilobite. A trilobite is a great index fossil because they existed anywhere between 544 to 251 million years ago. So if I find let's say a fossil of a trilobite, I know that whatever rock it is found in, or whatever area it's found in, that particular rock is going to be anywhere between 544 to 251 million years ago. And further down I find them, the older ones, right, the ones that are closer to the bottom of that rock layer are probably going to be closer to the 544 million years ago, as opposed to the trilobites, which are found further closer towards the top of that layer. I know those particular ones will be closer to 251 million years ago. So here's our dinosaur fossils, right? Dinosaur fossils are found anywhere between 251 to 65 million years ago. So if I look into a rock layer and I find a rock layer that contains a dinosaur fossil, then I know that dinosaur fossil existed 251 to 65 million years ago. And again, go back to your laws of superposition, the dinosaur fossils that are found towards the higher layers in rock, right, are going to be the ones that are closer to 65 million years ago because they're the younger ones. Now, thought question. If I find a dinosaur fossil and a trilobite fossil in the same layer, what do I know happened? What I want you to do is, if you're listening to this, is in the comments for this video, I want you to put down what you think would happen, all right, or what do you think is going on? So again, the question is, if you found the trilobite fossil and a dinosaur fossil in the same layer, what does that tell you happened, or could have happened, or may have happened? All right, pause the video, put the comment in, and come back. I'll wait. Okay, so you're back. I hope you did that. All right, I hope you did it, okay? So let's talk a little about correlation here. So example, all right? So there was a lava flow that existed here about 450 million years ago, took out a big chunk of this particular area here, right? This rock layer got destroyed, and what was left behind was this column over here and this column over here. Now, if I just went to look here and I just assumed that everything here was the same as what's over here. Well, first of all, the little lines here tell us that this is a shale rock. Okay, so that's what these lines represent. So this is shale, that's shale, that's shale, and that's shale. Well, how do I know that this layer is relatively the same age as this layer? Well, I know because there's index fossils. I see these index fossils that are known to be Ordovician, which is one of our major time periods. All right, this is an index fossil. And this means that this particular layer was 450 to 480 million years ago. But why is it so lower down? Just the way that this particular layer formed as opposed to this one. This was a lava flow and this one had other layers built on top of it. So again, we just look to see what are our index fossils, where are they found, and then we make that correlation that if this is in one spot, it's understood that it has to be relatively the same age because those fossils only existed at that time period for that amount of time. Okay, so to be considered a really good index fossil, you have to meet two criteria. The first is the organism had to exist over a very large geographic area, and the second it being that it had to have existed over a short period of time. Now, a short period of time is different from what you would assume a short period of time would be. Short period of time would be something along the lines of like 50 million years, right? That's a short period of time. All right, so there's only a small distribution. If we pick something that was around for 700 million years, that's too big of a gap. We can't narrow it down then, right? So we want to have something that existed for a relatively short period of time because it makes it easier to narrow it down. It's a lot easier to find I'll give you an example. It's a lot easier to find a section in a book out of 200 pages that you're looking for versus 700 pages, right? So the shorter the amount of time, the less areas you have to search to try and figure out where that particular fossil came from. All right, geologic time markers. These are deposits spread over large areas. a specific date. Examples can be things like volcanic ash, meteorite impacts. I'm not going to spend a huge amount of time on this, but there was something about 65 million years ago, the KT asteroid. The KT asteroid is what is theorized to have caused the extinction of the dinosaurs. So this gigantic meteorite struck somewhere around the neighborhood of Central South America. And how do we know that? Well, we know because of the change in the rock composition that existed here. And that's where we know 65 million years ago is when the meteorite hit, had to have hit because there was a change in the composition of those boundaries. Okay, so there's your KT boundary right there. All right, one last thing. Talk a little bit about Krakatoa. Krakatoa was at one point a very active volcano. In around 1883, it deposited volcanic ash, and that spread over over many miles, and deposited volcanic ash. Now, what happened is that created a boundary or a layer, and then more rock layers built up on top of that. But if we go back, we can see exactly where the layer of volcanic ash was that occurred from Krakatoa, and we know that if it erupted the last time in 1883, then whatever layer we're looking at had to have been from that time period. Okay, so I'm going to stop here, make myself a little bit bigger for a moment. So when we talk about all this idea of relative dating, it is an inexact science, but it is founded in ideas that make sense. All right, so that's the most important thing to remember. So in the worksheet that you're going to be doing, I'm going to give you some layers, and you're going to have to identify which is the youngest, which is the oldest layers. Okay, so you're going to want to look for a couple of different things. The first worksheet is going to be specifically on just identifying layers, and then in the second part of it, it's going to have something that shows index fossils in there. Okay, I'll put a little explanation video with all of that. Again, as always, if you need anything or if you want to rewatch the video, please rewatch this multiple times until you feel 100% certain on everything that you learned. Put any questions you have about the video into the comments section. Try to attend one of the Google Hangouts during the week. If you have any other questions, concerns, comments, or things you need to get in contact with me with, please just shoot me a quick email and I'll get back to you very, very quickly, all right? Stay safe, stay healthy, and I will talk to you all soon. Have a good one. Talk to you all later.